Good afternoon, everyone. Welcome back to week 2 assignment solving session. Today I'll be discussing the solution for week 1 and 2 assignments and some problems from week 2 lecture of the course. So let's start. The first question is the correct electronic configuration of element with atomic number 119 is option A is xenon 6x1, B is radon 7s1, C is radon 5s2, and D is uh, Ognition 8s1. So first we need to know which is the nearest inert gas present to this element to write the electronic configuration. So here is the periodic table, and we are given xenon, radon, and ognition. So from the periodic table, xenon is number 54, radon is 86, and ognition is 118. So the element with atomic number 118 is closer to 119. So the electronic configuration will start with OG. Then from OG is 118. So from 118 to become 119, we'll need one more electron. So it will be OG 8s1. So the option is option D. And the next question is the IUPAC name of the unknown element having atomic number 138 is. So the options are unbiquardium, B is untripendium, C is untrioctium, and D is unquad octium. So for naming any element, we need to know naming for each number of this atomic number. So the table is for 0, it's nil, for 1, it's un, 2, it's bi, for 3, it's tri, 4, quad, 5, pent, 6 is hex, 7 is sep, 8 is oct, and 9 is n. So whenever you are writing IUPAC name for an element, it should end with IUM. So the number we have is 1, 3, 8. So 1 is un, 3 is tri, and 8 is oct. So untrioctium. That's the IUPAC name for element having atomic number 138. So the option C is the answer. So the next question is the element with lowest ionization energy is. Option A is magnesium, B is barium, C is strontium, and D is calcium. So we need to know the position of these elements in the periodic table. So in the periodic table we have magnesium, barium, strontium, and calcium. So they are all present in the same group, group number 2. And we know that ionization energy decreases down the group and increases along a period. So when you move along a period, the effective ionization when you move along a period, the effective nuclear charge is increasing. So the energy required to remove an electron increases. And when you move down a group, electrons are having a low effective nuclear charge. So when you move down, the ionization energy becomes low. So in this group 2, barium is the in the given options, barium is at the bottom. So barium will be having lowest energy in this among these four. So option B, barium. The next question is among the following, the number of ionic species are uh, sodium chloride, methane, potassium iodide, uh, carbon dioxide, calcium chloride, magnesium oxide, PCl3, H2O, and SiO2. So to solve this problem, we need to know the electronegativities of each element, and in so if the electronegativity difference is above 1.7, that those elements will form ionic compounds. So the options given are among these only 3 are ionic, B is 4 are ionic, C is 6 of them are ionic compounds, and D is 5 of them are ionic compounds. So from this table, we can see the electronegativities, and for fluorine, it's the highest 4. And we are given sodium chloride. So sodium has electronegativity of 0.9. So sodium is 0.9, and chlorine is uh, 3. So the electronegativity difference will be 2.1. So delta electronegativity greater than 1.7 means they are ionic, and between 0.4 to 1.7 will be polar covalent. So NaCl has 2.1 electronegativity difference, which is greater than 1.7. So it's an ionic compound. And next one is CH4. In CH4, carbon is from here it's 2.5, and hydrogen is 2.1. So the difference is only 0.4. So it's a covalent molecule. Next one is potassium iodide. So potassium is 0.8, and iodine is 2.5. So it is 1.7. So it's ionic. Next one is CO2. So C is 2.5, and oxygen is 3.5. So the difference is 1. So it's not ionic. And next one is calcium chloride. Calcium is 1, and chlorine is 3. So the difference is 2. So it's an ionic compound. And next one is magnesium oxide. Magnesium is 1.2, and oxygen is 3. So the difference comes to 2.3, and it's greater than 1.7, so it's ionic. Next one is PCl3. Phosphorus is from here it's 2.1, and chlorine is 3, so it's 0.9. So it's not an ionic compound, it's covalent compound. Next one is water. So hydrogen is 2.1 and oxygen is 3.5, and the electronegativity difference is 1.4. So it's a polar covalent. It's not ionic. And last one is silicon oxide. So Si silicon is 1.8 and oxygen is 3.5. And difference is 1.7. So it will be covalent. It's not. Uh, so the answer is B. 4 compounds are ionic. And they are sodium chloride, potassium chloride, calcium chloride, and magnesium oxide. Next question is, among the following, the metalloid pair is option A is silicon aluminum, B is bismuth and tellurium, C is silicon and arsenic, and D is aluminum and germanium. So the for this we'll need to know again the periodic table and how the elements are arranged, and so metalloids are the elements showing characteristics of both metal and non-metals. So in periodic table in P block, and the metalloid separates both metals and the non-metals. So the diagonal elements, that is boron, silicon, germanium, arsenic, uh, antimony and tellurium, they will be forming the metalloid elements. So the option A is silicon and aluminum. So silicon is present in metalloids, but aluminum is not. And next one is bismuth and tellurium. Bismuth is a metal and tellurium is a metalloid, and given silicon and arsenic, so both are in metalloid. And last one was aluminum and germanium. Germanium is a metalloid, but aluminum is metal. So the option is C, where silicon and arsenic as the metalloid pair. And the next question is, the element having the largest atomic sizes. Option A is silicon, B is magnesium, C is phosphorus, and D is aluminum. So in the periodic table, we know that when you move across a period, the effective nuclear charge is increasing. So the size of the atom decreases. And when we move down a group, effective nuclear charge decrease. So size increases. So here we are given 4 elements: silicon, magnesium, phosphorus, and aluminum. So let's find it in the periodic table. So silicon, phosphorus, uh, aluminum, and magnesium. So all four elements are present in the same period. So when we move across a period, its effective nuclear charge increases, size decreases. So largest will be magnesium, then aluminum, then silicon, then phosphorus. Phosphorus will be the smallest and magnesium will be the largest. So option B is the answer. Magnesium is the largest atomic. Magnesium has the largest atomic size among these four elements. Next question is ionic hydrates react with water to give. Option A is basic solution and H2. B is acidic solution and H2. C is hydronium salt and H2. And D is only neutral acidic solution. So to begin with, we should know that there are four different types of hydrates, such as molecular, then saline. Third one is metallic, and finally intermediate. So the saline hydrates are formed by electropositive elements of group 1 and group 2, and they are ionic liquids with high melting point. And the group 1 and group 2 elements are less electronegative than hydrogen. So group 1 and 2 elements are less electronegative than hydrogen. So there is a large electronegativity difference between group 1 and 2 elements and hydrogen. So they form ionic hydrates. So the bond is ionic, and it will be represented as M plus and H minus. And these hydrates react with water, giving hydrogen gas and basic solution of hydroxide. So the reaction will be MH plus H2 giving H2 plus MOH. So the answer will be option A, basic solution and H2. So the example for saline is group 1 and 2 hydrate. For molecular, it's hydrates of p block elements. And for metallic, they are hydrates of D block. And fourth one is intermediate, and they are hydrates of beryllium, magnesium, aluminum, copper, and zinc. Next question is the radii of iodine species follow the order. A is I greater than I plus greater than I minus. B is I greater than I minus greater than I plus. C is I plus greater than I minus greater than I. And D is I minus greater than I greater than I plus. So we had discussed a similar question in the previous session. So when an element becomes an anion, or when we add an electron, that is when we add electron to I, it becomes I minus, that is anion. So when an element becomes its anion, its effective nuclear charge is lower than that of the original atom. So as the Z effective decreases, atomic size, that is ionic size, increases. Oh, that is radius of I minus is greater than I. And next one is I plus. So I plus means one electron is removed from I. That is I giving plus one electron. So it's a cation. So when a cation is formed, effective nuclear charge increases. So as the effective nuclear charge increases, ionic size reduces. So the order of radius will be I plus will be less than that of I. So if we combine, it will be I minus greater than I greater than I plus. So the option D is the correct answer. The next question is, according to Lewis structure, ClO3 minus contains n number of lone pairs and m number of double bonds. Option A is 8 and 2, B is 10 and 0, C is 10 and 3, D is 3 and 1. So uh, in Lewis structure concept, uh, it states that an element is stable when it has completed its octet. So bonding is done in such a way that each element has 8 electrons in its valence. So we can take chlorine as the central atom. So chlorine has 7 electrons. So we can 1, 2, 3, 4, 5, 6, and 7. Chlorine has 7 valence electrons, and we have 3 oxygen and 1 negative charge. So we can give oxygens here. So here chlorine is already having 7 electrons, so it needs only one more electron to become octet. So we'll add the oxygen with one extra electron to here, such that it shares that one electron with chlorine to form this complete its octet of chlorine. So oxygen with negative charge. So oxygen has 6 electron in its valence. So if we add one more electron, it becomes 7. So we are discussing question number 9, and so chlorine is the central atom, and oxygen has 6 valence, and there is one extra electron. So we'll give it to one of the oxygen so that this oxygen becomes the negative, and it's shared with chlorine, and chlorine has 7 valence electrons, and there are 2 more oxygens. So one having 6 electrons, and another one also having 6 more valence electrons. So if we form bonds like this, so now the octet of chlorine is completed, and Uh, yes, Sushma. Uh, Hello. Am I audible? Okay. Shall I start again this question or okay? I'll start from the beginning. So I'll start from the beginning. So chlorine has 7 electrons in its valence, and there are 3 oxygens, and one oxygen has one negative charge. So according to Lewis structure principle, so each atom is expected to have 8 valence electrons to form a stable compound. So we'll form a bond between shared bond between one of the oxygen that is having one extra electron. So this one will be the negative. This one extra electron will be the negative charge, and next oxygen will be having 6 valence electrons, and the next one will be having 6 valence electrons. So this is the octet of chlorine, and this will be the octet for one of the oxygen. This will be the octet for another oxygen, and this is the octet for a third oxygen. So we'll count the lone pairs. So this is the 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So there are total of 10 lone pairs, and in Lewis concept, there is no double bonds present between chlorine and oxygen in Cl3 minus. So 0 double bonds. So the answer will be 10 and 0. Uh, the next question is the steric number for xenon fluoride is. So in option A is 4, B is 7, C is 6, and D is 5. So in xenon fluoride, xenon is the central atom, and it has 8 valence electrons, and it forms 6 bonds with 6 fluorine. So 1, 2, 3, 4, 5, and 6. So there are total of 6 bond pairs plus 1 lone pair. So the total steric number will be 7. And for steric number 7, the expected structure is a pentagonal bipyramidal. Oh, Is it visible now? Okay. Uh, do you want to explain this again? Okay. So the geometry would be pentagonal bipyramidal. But the shape will be, yeah, but geometry will be pentagonal bipyramidal, but shape will be pentagonal pyramidal. So the option B is the answer. And next question is, so the next question is, the species that has 120-degree bond angles is NCl3, B is PH3, C is BCl3, and D is ClF3. So for NCl3, nitrogen has 5 valence electrons, and each will be forming bond with chlorine. So 3 bonds with chlorine and 1 lone pair. So it will be pyramidal shape, and for pyramidal it will be less than 109 degree. Okay, for PHT, similar way, 5 valence electrons and pyramidal shape will be there. So it will be again less than 109. And for BCl3, 3 valence electrons and 3 bonds are formed. So it's a perfect geometry. So it has a bond angle of 120 degree. And since there is no lone pairs present, it will be a perfect 120. And for ClF3, chlorine has 7 valence electrons and it forms 3 bonds with 3 fluorine. So it has a 5, steric number is 5. So steric number 5 and 2 lone pairs. So it will be a T shape. 2 lone pairs on the equatorial axis and 1 bond on one of the equatorial and 2 bonds on the axial position. So the bond angle will be 90 degree. So the only one with the 120 degree angle is PC. So option C is the answer. Okay. So the next question is, the molecule having linear shape and uh, linear geometry is. So in here it's I3 minus. So I having 7 electrons in valence and 1 negative charge is there. So we'll add that. So it will become 8 valence electrons. So and 2 bonds with 2I. So it will be 5 plus 2. So steric number is 5. And so it will be, we'll expect trigonal bipyramidal geometry. So 2 lone pairs on the equatorial position, 3 lone pairs on the equatorial, and two bonds formed on the axis. So it's a linear geometry. Uh, no, geometry is TBP, trigonal bipyramidal, and shape is linear. And next one is NO2 minus. So nitrogen has five valence electrons. So one negative charge is added. So we'll add it here. So total of 6 valence electron, and we have two oxygen. So two oxygen forming two uh, double bonds. So it's a total of steric number of 3, one lone pair and two bond pairs. So for expected geometry is trigonal planar, and shape is bent. And next one is NO plus. So NO plus, one electron is missing. So valence electron will be total of 4, and it has two oxygens. So two oxygens and no lone pairs present. So steric number is 2. So since there is no lone pairs, it will be a linear shape. So geometry linear, and it's the same as the shape. Last one is O3. Oxygen has 6 electrons in its valence and forms two bonds with other oxygens. So steric number is 3, that is 2 bonds and 1 lone pair. And expected geometry is trigonal planar, and shape is bent. So the question is molecule having linear shape and linear geometry. So the NO2 plus is the one with both shape and geometry as linear. So option C is the answer. And the next question is the compound having all bond angles exactly 109 degree 28 minute is. Option A is chloroform, B is carbon tetrachloride, C is iodoform, and D is dichloromethyl. So in chloroform, the chemical formula is CH3Cl, carbon tetrachloride is CCl4, iodoform is CH3I, and dichloromethane is CH2Cl2. So in CH3Cl, one bond is chlorine and other 3 bond with hydrogen. And carbon tetrachloride is C, and all 4 bonds are chlorine. And iodoform is uh, one bond with iodine or others with hydrogen. And dichloromethane, carbon, and 2 chlorine and 2 hydrogen. So here, according to Ben's rule, more electronegative substituents prefer hybrid orbitals having less s character, and more electropositive substitute prefers orbital having more s character. Or otherwise, if there is electronegative atoms present in the compound, that electronegative elements will attract uh, electrons in the bond towards it. So in this one, chlorine is more electronegative compared to this hydrogen. So this bond will be the electrons in this bond that will be closer to chlorine in this case. So one of the bond will be slightly deformed. So uh, when the electrons are moving away, there is more space around this carbon. So this angles can be larger than 109. So here also it's the same case, but compared to chlorine, iodine is less electronegative. So the electrons will be in the middle of this carbon and iodine. So the bond angle between HCI will increase compared to HCH, but it will be less than compared to HCl. And here two more Cl is present. They are more electronegative, so electrons will be closer to chlorine. So this bond will be able to move more, so the angles will become higher. In this case, all the uh, atoms are same, bonded atoms are same, so it will have perfect geometry. So in perfect geometry, tetrahedral will have 109 degree 28 minutes. So option B, that is carbon tetrachloride having all bonds with carbon and chlorine, it will have 109 degree 28 minutes. And the next question is the carbon atom in formaldehyde is A is sp3 hybridized, B is sp2 hybridized, C is sp hybridized, and D is unhybridized. So first we'll write down the structure for formaldehyde, that is H, C double bond O, and one single bond to H. So it forms a double bond with oxygen, which means uh, carbon in its ground state, it has 4 electrons in 2s and 2p. So in 2s 2 electrons and in 2p 1 electron each. And when it goes to excited state, when it forms bond with hydrogen and oxygen, one of the electron from S goes to one of the vacant p orbital. So 2s and 2p, one electron in each of the p orbital. So we should note that there is a pi bond forming. So to form a pi bond with one of the oxygen, it will need one unhybrid p orbital. So when we keep one of the p orbital as unhybridized, becomes sp2 hybridized. So it will be carbon, and it will have 3 hybrid orbitals, that is 3 sp2 hybrid orbitals, 3 sp hybridized orbitals, and oxygen is there. So oxygen has 2pz, so it forms a bond with the one of the hybrid orbital, which is the sigma, and two other hydrogen form sigma bonds, and carbon has one unhybrid p orbital. So if this is a 2px orbital, oxygen will also have a 2px orbital. So those two orbitals overlap sideways and form one pi bond. So it satisfies one sigma, and if this is the sigma bond and this is the pi bond, we'll get this sigma and pi bond of CO. So the answer is option B, sp2 hybridized orbital of uh, formaldehyde. And next question is the geometry of IOF is A is linear, B is trigonal planar, C is tetrahedral, and D is pyramidal. So IOF, I has 7 electron in valence. Uh, we'll go with oxygen as the central atom. So oxygen, and it has 6 valence electron and forms 2 bonds, with one with iodine and another with fluorine. And here steric number will be 4, that is 2 lone pairs and 2 bond pairs. So here the geometry will be tetrahedral. Since there are steric number is 4, then its tetrahedral shape will be bent. So option C is the answer. So the next question is isostructural pair is. So first one is SnF2 and second one is H2. So tin is in the group of carbon. So 4 valence electrons are present and it forms 2 bonds with fluorine. So it has 1 lone pair and 2 bond pairs. So steric number is 3 and shape will be bent. And next one is H2O, where oxygen is the central atom. It has 6 valence electrons and forms 2 bonds with 2 hydrogen. And the steric number is 4. It has a bent switch. Next one is PO4 3 minus, where P has 5 uh, 5 valence electron and forms bond with 4 oxygens. And there are 3 negative charges. So we'll add it to oxygen. So it will be 2, 4, 5, 6 and 7. So this will be O minus, and a double bond O. Next one is SO4 2 minus. Here steric number is 4 and structure is tetrahedral. In SO4 2 minus, sulfur has 6 6 valence electrons. So it will form so SO4 2 minus forms double bond O, 2 double bond O's and O minus and bond with 2 O minus. So steric number is 4 and structure is tetrahedral. And C is IF2 plus and I3 minus. So IF2 plus is iodine having 7 valence electrons, but if we add the positive charge to iodine, it will become 6 valence electrons. So 6 valence electron and 2 fluorine bonds. So it will be bent as steric number 4 and bent structure. In I3 minus iodine having 7 valence electron, but if we add that negative charge to central metal, central element, then it becomes 8 valence electron, then 2 bonds with 2 iodines. So it will be a steric number 5 and linear shape. And in CO2, 4 valence electron and it forms 2 double bond with oxygen. So it will be linear. Steric number is 2. And SF2 2 minus, sulfur has originally 6 valence electrons and 2 minus charges are added, so 8 valence electrons. So and 2 fluorine atoms are bonded, so it will be linear with steric number 5. So option B is the answer, where both PO4 3 minus and SO4 2 minus having tetrahedral structures. And the 17th question is, s orbital are non-directional because of option A is their small size, B being a first orbital and zero screening constant, C spherical symmetry, and D is non-spherical symmetry. So this direct question. S orbital is always spherical, and but for P there is dumbbell shape, and they are oriented in different axes. So if this is pxy, px, there will be another orbital which is pz, and another one py. So p orbitals are directional. So it has 3 different orientations: px, pz, and py. In s orbital, it always spherical, so it is non-directional. So option C is the answer, spherical symmetry. And next question is, a molecule of fluorine is formed by, option A is the axial pp orbital overlap, B is the sidewise pp orbital overlap, and C is the axial ss orbital overlap, and D is the axial sp orbital overlap. So we don't need to consider the hybridization here. We can go with the valence electrons. So in FF we expect a single bond. So fluorine has 7 valence electron. So 6 it will remain as the lone pairs, and one will be shared and forming a covalent bond between fluorine and fluorine. So one fluorine has 2s and 2p. So 7 valence electrons. So this orbital, that is if it is 2pz, they will overlap sidewise in the axis. So if this is the fluorine 2p set, it will bond with other orbital of fluorine. So there is 2 electrons in the opposite direction. So 2p sets of fluorine will overlap and form the bond between fluorine and fluorine. So the answer is the axial pp orbital overlap of fluorine. The next question is, among NF3, NH3 and NCl3, which one has the largest bond angle? So nitrogen having 5 valence electrons, and forms 3 bond between fluorine, similar to that hydrogen forms to form ammonia. And next one is chlorine. So we have already seen similar example. So fluorine will have more higher electronegativity compared to nitrogen. So the electrons in this bond will be closer to the fluorine. So there is more space between this nitrogen and the bond. So the angle will be low. So here chlorine is more electronegative than nitrogen. So that electrons will be closer to chlorine, but it won't be as close as to fluorine. Because chlorine is less electronegative compared to fluorine. So the bond angle will be medium. Here nitrogen is more electronegative compared to hydrogen. So electrons will be closer to nitrogen. So to minimize repulsion, the bond angle will be higher in the case of NHH. So this will be the highest. So option C is the answer, where NH3 has largest bond angle. And the next question is, the pair with same bond order is. So we'll start with the O2 plus. So in O2 plus, there are 11 valence electrons, which means in one oxygen is remains as oxygen, the other one is O2 plus. So we'll write the molecular orbital structures. So first one is 2s and 2p. So oxygen has 6 valence electrons. Is 4 oxygen, and 1 electron less for O plus. So these two forms sigma 2s, sigma star 2s, and these two will be uh, sigma 2p and pi 2p, then pi star 2p and sigma star 2p. So there are total of 4 plus 3 7 electrons, 2 6 and 1 electron in the antibonding orbital. So the bond order will be these two will be cancelled out. So 6 in bonding minus 1 in the antibonding orbital, that is 2.5. And in NO plus there are 10 valence electrons, nitrogen has 5 valence electrons and oxygen has 6. And since there is one positive charge, we'll add that to oxygen. So oxygen will be having 5 valence electrons. So if they form molecular orbitals, so there are total of 6 electrons and they will be added in pi 2p and sigma 2p. So the bond order will be 6 minus 0 by 2. This 3. So here the bond order is for O2 plus was 2.5 and for NO plus it comes to 3. And in N2 uh, we can change here. So if these are 2 nitrogens, so the valence electrons are 5. So in atomic orbitals in 2s there is 2 and in 2p there are 3 electrons for nitrogen. So when molecular orbitals are formed, 2 electron goes to sigma 2s and 2 goes to sigma star 2s and the bond order calculation will be cancelled for these two because there are equal number of electrons in bonding and non-bonding orbitals. So for 2p there are 3 electrons in each nitrogen 2p orbitals and they are filled in pi 2p and sigma 2p and there are 6 electrons. So bond order will be 6 minus 0 by 2, that is 3, 4 and 2. And in case of oxygen, so we can here we'll write for oxygen. So in oxygen there are 12 valence electrons. So there are 6 valence electron for one oxygen. So two s combined to give one sigma 2s and one sigma star 2s. And this P will be forming sigma 2pz and pi 2p. And anti-bonding will be pi star and sigma star. So we'll add the electrons. Here 4 plus 4, 8 electrons are present. So we'll add that in sigma 2pz, pi 2p and pi star 2p. So in O2, the bond order will be, these two will be cancelled out. In bonding orbital, there are 6 electrons, and in antibonding, 2 electrons are present. So it will be 6 minus 2 will be 4 by, and 4 by 2 is 2. So bond order is 2. So next is O2 2 minus, and in O2 2 minus, there are 14 valence electrons. So that means in each O minus will have 7 valence electrons. So we can add the other electron here, and so we will have 2s2 2p 5 configuration. So if this is O minus, we'll have sigma 2s, sigma star 2s, sigma 2pz, pi 2p and pi star 2p. So here if we consider 2p, there are 10 electrons total. So 2 here, 2. In pi 2p, 4 electrons will be there. So 2, 4, 6. Then in pi star 2p, there will be total of 4 electrons. So 10 electrons in sigma 2pz, pi 2p and pi star 2p. So bond order will be 6 minus 4 by 2. So 2 by 2 is 1. So bond order becomes 1. In B2, There are a total of 6 valence electrons. 1B will be having 3 electrons. So it means so 2p will be having only 1 electron. So there are only 2 electrons present in the 2p. So 1 electron will be uh, equally distributed in the 2 uh, pi 2p orbitals. So the bond order will be these two will be cancelled out, and only electrons in pi 2p is present. So it will be 2 by 2. So, so in B2 it is 1, and next one is NO. In NO there are 11 valence electrons. So this forms sigma and sigma star. This will form sigma 2p. So a total of 7 4 plus 3 7 electrons are there. So in sigma 2p, pi 2p, and 1 uh, pi star. So the bond order will be 6 minus 1 by 2, 2.5. And the other molecule is carbon monoxide, CO. It has 10 electrons and it is similar to nitrogen. So in carbon, there are total of 4 valence electrons, and in oxygen, there are total of 6 valence electrons. So 4 plus 2, 6 electrons are there. So we'll add in uh, pi 2p and sigma 2. So the bond order will be 6 minus 2 by 2 is 3. So for NO it's 2.5 and then CO it's 3. So the question was the pair with same bond order is. So option C, it's O2, 2 minus and B2 are having same bond order. So answer is option C. The next question is in O2, the number of electrons in pi star antibonding orbitals and the bond order respectively are. So O2 has 12 valence electrons. One oxygen is 2s2, 2p, O. So So in 2p there are total of 8 electrons. So we'll add it in sigma 2p, 4 in pi 2p, and 2 in pi star 2p. So the bond order will be we can cancel these two, and for sigma and pi p's, uh, 6 in bonding orbitals and 2 in antibonding molecular orbitals. So 6 minus 2 is 4, 4 by 2, that is 2. So the question is number of electrons in pi star antibonding orbital, that is in pi star there are 2 electrons, and the bond order is we got 2. So option D is the answer. And the next question is the correct order of the decreasing bond energy for the given species is. So bond energy we can calculate by finding out the bond order. So bond order and bond energies are directly proportional. So for N2 uh, we have 10 valence electrons in N2 plus. We have 9 valence electrons, and in O2 there are 12 valence electrons. So we can do the molecular orbital for each of these. So first we'll do the N2. In N2 there are 10 valence electrons. So uh, there are 2 electrons in 2s and 3 electrons in 2p. And similarly the next nitrogen. So total of 6 electrons. We'll add in pi 2p and sigma 2p. So the bond order is 6 by 2, that is 3. And in the next case N2 plus. So in N2 plus we can remove one of the electron from this sigma 2p. So if we remove one electron from sigma 2p, it will be sigma 2p 1, since one of the nitrogen is N plus, so one nitrogen will be having only 2 electrons in 2p. So the bond order will become total of 5 electrons in 2p molecular orbitals, that is 4 in pi 2p and 1 in sigma 2p. So 5 by 2 is 2.5. In O2, the energy order of these molecular orbitals are different. So oxygen has 6 valence electrons, 2 in 2s and 4 in 2p. So in molecular orbitals, there are 8 electrons, 2, 4, 6 and 8. So here the bond order will be, we can cancel this out, and for sigma 2p and pi 2p there are 6 electrons, and in antibonding orbital there are 2 electrons. This 4 by 2, this 2. So the bond order is 2. So we got for nitrogen uh, N2 plus and O2. The bond order is N2 3, N2 plus is 2.5 and O2 is 2. So we have already stated that bond order is directly proportional to bond energy. So bond energy will be in the order of highest bond order will be having highest bond energy. So N2 will be higher than N2 plus than O2. So the answer is option D. The next question is the correct order of increasing bond angle is. So in there are 3 molecules, ClO4 minus, ClO3 minus and ClO2 minus. So chlorine has 7 valence electrons, and in all of them there is one negative charge. So if we include it in chlorine, it will become 8 valence electrons. So 8 valence electrons, and then ClO4 minus 4 oxygen forming bonds. So double bond O, double bond O, double bond O, and double bond O. We'll be having a tetrahedral shape and 109 degree 28 minute bond angle. Next one is ClO3 minus. So chlorine with 8 valence electrons because of this extra negative charge and forms bond with 3 oxygen. So 1 oxygen, 2 and 3. So one lone pair is present. So the structure is pyramidal, and the angle will be less than that of 109 degree because the lone pair will have more repulsion than the bond pair. So it will, the molecule will try to minimize that repulsion by uh, forming closer bond angle of OClO. So this is less than 109, and next one is ClO2 minus chlorine has 8 electrons in valence because of the negative charge and forms 2 double bond O. So now there is 2 lone pairs present. So here, because of this 2 lone pairs, the repulsion will be more than this pyramidal structure. So the bond angle will be less than that of ClO3 minus. So it is because bond pair repulsion is less than bond pair lone pair repulsion less than lone pair repulsion. That is, higher the number of lone pairs, the repulsion will be really high between these two, so that angle between these two will be higher. So these two has to go lower because of bond pair repulsion is lower. So the bond angles will be uh, higher for ClO4 minus, then ClO3 minus, then ClO2 minus. So the option D is the answer. ClO4 minus has the largest bond because of it has no lone pairs, so it will form a tetrahedral structure with 109 degree. And the next question is the number of electrons present in the pi star orbitals of NO plus in its MO diagram and the bond angle, bond order respectively are. So we have already seen, but we'll do it again. In NO plus, total of 10 valence electrons are present. So in nitrogen, 5 valence electrons, and in O plus, there are 5 valence electrons. So total of 6 electrons, we'll add it in pi 2p and sigma 2p. So the bond order is 6 minus 0 by 2, that is 3. So the question is pi star electrons present in pi star. So in pi star it's vacant, no electrons are present. So 0 electrons in pi star orbitals, and bond order is 3. So option A is the answer. Next question is the correct order of uh, molecular orbital energy levels for O2 molecule is. So if you have watched the lecture video, you will see that there are two possibilities for B2, C2 and up to nitrogen, that is up to uh, 10 valence electrons. And the second case is for uh, oxygen and the elements having more than uh, 12 valence electrons. That is O2, F2, and Ne2. So up to nitrogen, the molecular orbital formed by the 2p mixing is uh, pi 2b having lower energy than sigma 2p, and from oxygen the order reverses so that sigma 2p having lower energy compared to pi 2p. So the order will be sigma 2s less than sigma star 2s for O2 molecule. Then sigma 2p, then pi 2p, then pi star 2p, and then sigma star 2p. So the answer is option D. So if you have any doubts, you can ask. Yeah, yeah. Good evening, Prabhat. Okay. Okay, this one. Okay. If we put iodine as the center, so I think we'll get the similar geometry. Um, so iodine, yeah. If we put iodine, iodine has 7 valence electrons, and it will form one bond with one of the fluorine and form two bond with oxygen. So the geometry does not change if we change the central metal atom also in this case. Uh, mm, that depends on which which atom we are choosing at the central atom. So I think this one will be more appropriate because as you have said, uh, the electronegativity of fluorine and oxygen is high. So central atom we can choose as iodine. Okay. For this question, uh, what is the rule? Uh, no, in formaldehyde, carbon is bonded to oxygen, and so we'll need to complete the valency of carbon, no? So it will form bond with a hydrogen. So this is the actual structure of formaldehyde. In this question, this is the actual structure. If we form bond with COH, this will be an alcohol, and the formula will be like this, and the valency will not be satisfied for carbon. 2 electron will be remaining. Okay. Sidewise overlap means if the p orbitals are orienting like this, so sidewise will be like this. So that will be a pi bond. So a molecule will be first forming a sigma bond, then only it will consider forming a pi bond. This one, you are talking, this is a sidewise overlapping. Is that the doubt? Uh, no, actually, this is the axial. Yeah, the answer is axial. Yeah. No, no, it's axial. Okay, thank you.